Welcome GeoTrig. This is 4.6, Graphs of Other Trigonometric Functions. Let's begin. So we're going to go over all the other ones we didn't do in the last video, so tangent, cotangent, cosecant, and secant functions. First one, we'll start with this tangent function. So tangent function looks like this. The neat thing, these are different, is you always have these vertical asymptotes here. So the periods of the tangent function is pi, not 2 pi this time, just pi. Tangent's an odd function, okay. And the tangent function is undefined, so it's asymptote at x equals -2, or x equals pi over 2. I also have a vertical asymptote at negative pi over 2. If you notice, you're looking at a unicircle, the x value is the angle, the y value here is your tangent, so the sine over the cosine of that angle. So if you followed a unicircle, you get the same numbers. Now, some other properties about this, again, the period's pi. Domain is all real numbers except odd multiples of pi over 2, so except the asymptotes. And the range is all real numbers because it's going down and up forever. Vertical asymptotes are at odd multiples of pi over 2. X-intercept occurs midway between each pair of consecutive asymptotes. So if you had asymptotes, the halvesies part is right here, and this is your x-intercepts. So all at the halvesies parts. Odd function, okay. Points in the graph 1/4 and 3/4 away between consecutive asymptotes have y-coordinates of -1 and 1. So that's saying that you can figure out these points right here, and it's actually based off the amplitude of the function. So that's the basic idea of when you're graphing these is you're going to be graphing 3 points and find the asymptotes. So to say that in the steps, you want to find 2 consecutive asymptotes that form in the interval. So basically you take the inside the function, the bx minus c. You figure out the points where bx minus c equals negative pi over 2 and positive pi over 2. Another way to say that, bx minus c equals plus or minus pi over 2. So these are going to be your asymptotes. So that's a key part to actually find the asymptotes. Identify an x-intercept. So that's halvesies. Halvesies. I'm going to say halvesies. So the halfway between the asymptotes is the x-intercept. So plot that point. Boom. Now this other part I crossed off. So finding those points, the 1/4 and 3/4 of the way through, and it's based off your amplitude, -a and +a. So that's what's saying these 2 points right here. So if you find halvesies part, the halvesies of the halvesies and the asymptotes, that's going to be another point. So you can do 3 points to get a good shape of the curve, and it's based off the a. Now, as long as you get these asymptotes in this middle point, these other points I don't think they're that critical. But being able to find the asymptotes and then get the halfway point and then know that the shape is going from a negative side to a positive side, so it's kind of increasing, that's the key part here. You got to be increasing. So make sure your curve is increasing and you got the asymptotes. So let's try one of these. So I want to graph this function y equals 3 tangent of 2x. So your amplitude is going to be 3. And now you got to figure out the asymptotes are. And like I said before, your asymptotes are when bx plus c is plus or minus pi over 2. So in this case, there is no plus c. It's just 2x equals plus or minus pi over 2. So another way to say this, I'm going to divide both sides by 2. And so you're going to get x equals plus or minus pi over 4. These are the asymptotes right here. So I'm going to actually draw those asymptotes in. Oh, I erased everything. So if this was pi over 4, I'm going to change that to be pi over 4. I'm going to change this to be positive pi over 4. This is going to be pi over 2. And this is going to be 3 pi over 4. Just to get our scales easier to see. So that means I have an asymptote. Let's right here. So I'm drawing my perfectly straight asymptote. And I have another one right here. Okay, so I got my asymptotes. And now I know I have a part at the halvesies point, which is going to be at the origin. So that's my x-intercept. Now, what I can follow is the rule of the asymptotes, the 1/4 and 3/4 ways. Since the amplitude is 3, I know up here, there's going to be a point right here. That's 1/4 of the way up. And there's going to be a point down here at -3. So now that I got those 3 points, I got my asymptotes, I can draw my curve. So it should look like this. And that was not really a great curve. So if you're looking at the examples, you see that we have to have that the kind of U shapes. So let's see if I can do a better job. I'm going to connect it like this. Kind of like that. You need practice. And I need practice. But now I have to go to 3 pi over 4. Well, you're going to have asymptotes every same pi over 2 here. So I'm going to have another tangent function shape right here. Oh, that was a much better curve. So there you go. That's my graph between that interval. Let's talk about cotangent. So cotangent's kind of like tangent, except it's going to be decreasing. The period's the same. The domain is all real numbers except integral multiples of pi. So notice the tangents, or the asymptotes, are happening at 0 and pi, not pi over 2. And that's the key part to understand when we're actually graphing that. The vertical asymptotes are multiples of pi, x-intercept midway, same thing. Same thing about the odd, same thing about the points, quarter and 3/4. So to graph that, the difference here is you got your formula bx minus c, asymptotes at 0, and then bx minus c at pi. Instead of plus or minus pi over 2, it's 0 and pi. So that's the big difference. So let's actually graph one of those. So if I wanted to graph this, my amplitude here is 1/2, and then your asymptotes are going to be at bx plus c, so there's no plus c. So it's going to be pi over 2 x equals 0. So and then pi over 2 x equals pi. So for the first one, this is going to happen when x equals 0. That's the first asymptote. And the second asymptote, it's going to happen, multiply both sides of the equation by 2 over pi. And when you do that, these cancel and these pi's cancel, so it happens when x equals 2. So if I were actually drawing this graph, I'm going to change these x-axis labels. You're going to have it, let's say if that's 1, 2, 3, 4, so on. You're going to have the first asymptote x equals 0. So right here. And then x equals 2. Right here. Your middle point, halvesies, is going to be right there. So that's your x-intercept. And since the amplitude's 1/2 at the 3/4 points, we're going to go up half of 1, so it'll be right there. And then down half, it's going to be right there. So if I want to draw that curve, hey, I'm getting better at these. More practice, hey. So that's the one cycle of the tangent function, or cotangent. Next thing, cosecant and secant. You're just taking the reciprocal of the y values of sine and cosine. So it's the reciprocal of the sine and cosine functions. This is the cosecant function. This is the reciprocal of the sine, because cosecant's 1 over sine. So notice the dotted line here, this is the actual sine function. And the actual cosecant function is these U shapes. We have asymptotes at the x-intercepts because you can't, 1 over sine, you can't divide by 0. So whenever sine of 0 is 0, that's cosecant function is going to be undefined. So you will have those vertical asymptotes every multiple of pi. And yeah. The secant function is, secant is 1 over cosine of x. Notice again, you'll have some asymptotes wherever cosine function was going to equal 0, so at the x-intercepts. There'll be asymptotes. Alright, using the sine curve to obtain a cosecant curve. So one way to actually graph, if you want to graph a cosecant, is to graph the sine curve here. So it's easier to graph sine of x plus pi over 4, and that's in red. And then you just do the U shapes and the mountain shapes and do those asymptotes. It's easier just to graph the sine function first, then graph the cosecant or secant functions on top of those. Here's all the 6 trig functions having a big party. That's it.